to everybody. This is a new session of the webinar, the reservoir and the labs. Mr. Derry, the subject of this seminar is base of NMR and use of laboratory NMR to help interpreting NMR logging data. I think we can leave all the space to this seminar to Derry Green. Usual, this presentation will start now, and more or less this presentation more or less in 1 hour. After that, we're going to have a question and answer session. As usual, prepare to jot down your question via remote chats. I will read the question and I will provide reply. So we're going to have a discussion over here in the Mosaic room. Of course, all the attendees here will follow question and speakers will provide reply. I think we can start. Mr. Berg, please.
Okay. Much. Just to give background on myself, I'll introduce myself. I'm the Chief Technical Officer at Green Imaging Technologies, and our company, we write applications in the form of software for NMR laboratory equipment. Laboratory equipment is designed to help understand the reservoir fields and the logs and sorts of things. So my experience is in that area. I have degrees in electrical engineering and magnetic resonance imaging, and I've been the Chief Technical Officer for the last 6 years at Green Imaging. We'll just get going. We'll give an overview of core analysis techniques. I'll try to focus on how those core analysis techniques can be used to help understand the reservoir and NMR logs as well. So what we're trying to do is just understand the complete picture of the reservoir, and NMR fits into that picture. So this is a simplistic diagram of where analysis fits in the whole routine. The whole goal, of course, is to find oil and gas, but then, of course, to characterize the reservoir so we can predict production and know the reservoir size. And I see this as a cyclical program during the life of a reservoir. So some of you will be familiar with this, but core analysis fits here, defining the reservoir simulators or reservoir models. So NMR would fit in this portion of the cycle. So time describing NMR, even though the talk says the basics of NMR, I'm just going to do a few things that you need to understand in order to help understand NMR can apply to NMR logs and NMR core analysis. So components, first thing I'd like to say is MR, which is magnetic resonance imaging, and NR, which is nuclear magnetic resonance. They're the same thing. The medical field doesn't like the word nuclear, so it just magnetic resonance. So magnetic resonance imaging is typically used in medical fields. This is a metal scanner. These are magnetic field gradients. In other words, we alter the magnetic field in the sample, and we use frequency coils to place energy in and out of the system to detect the signals. And there's a lot of other components I won't really get into. But this is the basics of a machine. The equipment is quite different. So the diagram is a logging tool. It's probably quite an old logging tool at this point. NMR logging tool in which you drop it down the hole and do a wireline log. These NMR measurements that I'll describe in a few minutes. The lab equipment is quite different. It's desktop based. You can see, so these are some of the older models, but it's smaller to measure sort of 1.5-inch core plugs. You can have larger equipment to do whole core as well. So people care about NMR and core analysis, well, in medical for that matter. NMR is unique in that the signal we can get from NMR comes from hydrogen. So in simplest sense, anything with hydrogen, when we place it in a magnetic field, it will exhibit a property that allows us to detect how hydrogen's in that sample that's in the magnetic field. So in human beings, that's quite important because human beings are mostly water, so we can measure the water, the fat, all kinds of things. In oil and gas, of course, it's also quite important because we're interested in water and hydrocarbons, right? So gas and oil, so we can see those signals. So seeing how much hydrogen we have, which would be an important measurement in its own right, we can do other things with nuclear magnetic resonance, or NMR. We can localize that signal using 1D or 2D or 3D images, see where that hydrogen is in the sample, and that's what we do in human beings. When we take a picture of somebody's head, as shown here, we take an image of where that hydrogen is in the person's head. Core analysis, we often don't localize the signal. We're interested in the properties of the hydrogen, so the signal lifetimes. So if the signals we detect will have finite lifetimes, and times are known as things like T1, T2, and T2 star, and you've heard these from logging terms in NMR logs. But think of them as just simple signal lifetimes. And you have is these signal lifetimes depend on the environment of the hydrogen. So by environment, I mean what hydrogen is in a big pore versus a small pore, what hydrogen is attached to a small molecule or a big molecule, ability of those molecules, all kinds of different things. That's where we get the information from NMR. So just how much hydrogen, but we can tell something about the environment of hydrogen, and that's how NMR becomes a valuable tool. So tell us about rocks. There's a number of things that we can tell. Historically, NMR has been used to look at pore size distribution. So signal lifetime T2, if you will, what the pore size distribution is, and I'll describe that in a little more detail in a minute. You can get bound and free fluids, clay-bound fluids. People have developed permeability relationships associated with that. And the cornerstone of NMR use in the gas sector since it was invented by, I guess, the folks down at Newmar in the U.S. And can also be used for many other things, hydrocarbon typing. These are things that are newer. Porosity, in other words, mobility of the hydrogen by way of molecular diffusion. And again, I'll get into more details on some of these things in a few minutes. And I'm good wettability indicators. So whether hydrogen is in contact with the pole and whether that hydrogen is oil or water can be indicated by NMR as well. I'll describe a few advanced properties like how we can use NMR to assist in getting capillary pressure and those types of things. Very simple diagram on how NMR can help us get, say, the pore size distribution, because historically this is what NMR has been used for. So look at the signal. This is what I meant by signal lifetime. So this is the detected NMR signal that we detect. And the signal of hydrogen in a big pore will decay away very slowly. In other words, it will have a long signal lifetime. The small will have a short signal lifetime. What we measure is the summation of all of the pores. So this is the signal we actually measure with NMR at the bottom. So it is devolve or get that information back out of that signal. So what we want to know is what are the different quantities of signal lifetimes in that signal. And we do a thing called an inversion. You made this again from logging space, but this is the inversion we take to detect what we detect, the NMR signal, and into a distribution of exponential decays. In other words, a distribution of signal lifetimes. And this is math, and I won't get into the math, But suffice it to say, this process can be quite difficult, and in fact, with the last term here, it has many solutions. So what it does to converge on a solution is it adds an extra term. It's called a smoothing term, a regularization term, and this has led to some of the inconsistencies in the data because people will do this in different ways. What to do is we want to introduce a term that allows us to use dependencies on that exponential signal lifetime. So one thing to say is if pore size that's 1 micron in a pore, it's very likely that we'll have a pore size, at least some pores that are 1.1 micron, right? So we don't just have an impulse response of 1 micron pores. It's going to be a distribution of pores. So information to merge this solution. So that's what the smoothing term does, is it forces it forces solutions of neighbors to be related. Now, it forces the distribution to be smooth. And that's here. So in this example, we have large pores, medium-sized pores, and smaller pores. So if we see the equations involved, this is the T2 equation. So this is the signal lifetime T2. And it's an equation. It's a fluid. So this is the T2 property of fluid. Also depends on the surface to volume ratio of the pore. It also depends on the third term, which it depends on diffusion, which is the mobility of that T2, and fundamental parameter TE. I won't really describe what that is, but suffice it to say we can make that short so that we can ignore this term. The fluid is typically long, so this term dominates in this expression. Of course, what we want, so the T2 depends directly on the surface to volume ratio. So when we look at this axis, we can assume that this axis is translated directly into radius or pore size. So in the distribution, some here that are again and as we go left. Astrophysics will tell us that as the pore size gets smaller, the capillaries inside that pore will get higher. Get to a point where the capillary force cannot be overcome and that fluid will be bound in the pore. So we call it capillary fluid. So what these distributions is we apply and we see pores that are smaller than this are bound. All the pores that are larger than this are free. So we have, in essence, divide this distribution up into two pieces. One fluid, mobile fluid, and one being bound fluid. So where we place this line is quite critical. And I'll just how we can do laboratory measurements to assist in getting the cutoff. In logging tools, we'll use standards based on the lithology of the well. So for instance, sandstones use 33 milliseconds as a standard. It's used somewhere around 90 or 95. But in truth, that cut will depend on the reservoir. So laboratory measurements are obviously to ground those cutoffs. The process typically is to derive a permeability relationship from these MR measurements, and these were done by Schlumberger and Coates at Newmar a long time ago. And there's typically only two that I know of that are well used. One's called the Mean or Schlumberger model, and the other one's the free fluid model. The permeability based on the geometric mean of the T2, in other words, the average T2 value in the measurement I showed you above, and the coefficient, of course. On the ratio of free fluid to bound fluid, and coefficient, or sorry, a constant. It's called coefficient. In reservoirs, what we're able to do is divide this into free and bound fluid using a cutoff. If we have coefficient, we can derive permeability. And again, we'll do laboratory measurements to refine those values for particular reservoirs. In my experience, this first one typically only gas fields. When there's more than one fluid, the free fluid model tends to work better. But that's not always true. Logs, because you may have more experience viewing logs. I'll just a real quick log here, and this is a T2 distribution. Very simple sandstone reservoir, I believe. What we're able to do is we apply a cutoff, which is this red line, and we say everything over here is bound, everything over here is free. We then plot down a trace showing bound and free fluid, permeability relationships, and predict permeability. And for is a good correlation between this and laboratory measurements. So the logs, how do we calibrate these values in the laboratory? Well, we do this quite simply with a couple different T2 measurements, if you will. So we'll take them and we'll fully saturate the rock with brine, and we'll do a T2 measurement. And we'll do something like the yellow line. This yellow line is the pore size distribution because it has only one fluid and it's fully saturated. We'll remove all the free fluid, and a number of ways we can do that. We can spin it in a centrifuge to force that out. That's probably the simplest way. We could use flow cells, all sorts of different apparatus, but the centrifuge is typically the easiest way. So if we remove fluid and then do another NMR measurement, by definition what we're measuring is just the bound fluid. So the bound fluid is simply given by the area underneath this curve, or relative distribution. So the cumulative, I should have said earlier, is just the summation of this dark line point. So this represents all of the area underneath the blue curve. We have the free fluid, the difference, we have fluid, free fluid, and we cutoff value to represent area underneath the yellow curve to this line to equal the area underneath the whole blue curve, and that will be the cutoff. So the trick to do is to go back to the total cumulative till they hit the yellow cumulative and they come down. But basically it's the area underneath yellow to the line equaling underneath the whole blue line, and that is the cutoff. So cutoff for this specific rock, and of course we'll do many of them. We'll do statistical analysis to get an average value. In the example, you can see the cutoff is less than 10, and that's quite typical for tight gas fields. It will be substantially less than the 33 millisecond standard value. Around 10 in tighter fields is typical. What impact does that have on our analysis? And this is, again, a well in which we did a few different studies. The standard value will get a bound fluid given by value, which is very close actually to the porosity. So it's predicting the fluid is bound. When we measurements and refine that cutoff back to 10 milliseconds, we'll get bound fluid, so we actually have a lot large amounts of free fluid. And that's going to be important, right? So that's, in some instances, the free level, free fluid is predicted by almost a factor of 5. And this is substantial impact when you're analyzing your logs, laboratory measurements. As part of the process, we'll measure the permeability of each of these samples, and we'll derive those other permeability coefficients as well. I'll mention this because historically people have said that we don't see clays in these T2 measurements, and that's certainly been true. Based on equipment limitations, we really haven't seen the clay-bound fluid. They're called echo time or tau, but basically as the instruments have gotten better, we're able to decrease that measurement time, and we're not seeing clays in these things, and the instruments definitely will see clays. And then the logging tools will start to see clays. So you have to be cognizant of what is the actual porosity you're measuring. Is it effective porosity? Is it the total porosity? Is it an NMR porosity? So you have to be a little bit careful because the NMR porosity will include typically clays. And you typically want to consider these in the porosity. just something to be considerate of in some of the newer pieces of equipment. What we often do is we'll apply cutoff somewhere and say the fluids with short T2s are clay. We've laboratory measurements to ground that, because we can measure the clays quite easily in the laboratory. We do different types of rocks. The NMR measurement works in almost all types of rocks. We've done, have done, not just us, regular sandstones and carbonates, of course, but our work is more recent. Oil sands, particularly with new equipment, the oil sands are showing some promise because we're able to see some of that heavier oil that we couldn't in previous generations of equipment. This example, a little bit, there's some more complex NMR measurement, but the NMR I think is showing a lot of promise and giving us some insight into shales. In this example, we can see some of the fracture network was done with pressure. So if you added confining pressure, the fracture network would close up and you wouldn't see it. So the fracture network appears as longer T2s because it has a large pore. That the situation can be quite complex. So one thing people will say is NMR is a very powerful tool, and that's true, and the reason true is because NMR is sensitive to many, many different things. So it's sensitive to viscosity, it's sensitive to wettability, it's sensitive to how much hydrogen, lots of things. Well, the biggest problem is it's sensitive to a whole bunch of things, right? So how do I get just one property out of it when all of these things tend to overlap? So I've kind of shown that graphical is first presented by Coates in his book. You may have seen it. But what we hear, of course, what we measure in an NMR sense on these distributions is the envelope of these two things. I've just shown what is contributing by the oil and the water, by the different colors, the water being blue. Oil, water, wet case, we would apply a cutoff here. We'd say fluid to the left of that is bound, all the fluid to the right is now, and a light oil, water, wet case. As we move to heavier and heavier oils, we're going to end up with a situation where that's no longer true. So we'd apply off in the same location, but now exist as short T2 values because the T2 is on the fluid, not only pore size, but the fluid as well. So some of the heavy oil, if not all of it, will be predicted to be bound, and that can lead to a misinterpretation, because indeed that heavy oil will move. This is the same problem. When we go back to an oil wet case, we're okay because the fluid that's in those capillary bound is now oil. But again, heavy oil is generally always a problem. Next wet case. This as a problem, but it's also an advantage as well. That then the wettability and viscosity as well. So we can introduce more complicated measurements to try to get information out. And what with this example is just show you how the NMR would change with the wettability of a rock. So what are we looking at here? Well, a pore in which it's water. In other words, water is out here along the pore wall, and the oil is in the center of the pore. In an idealized sense, you'll never measure this, but in an idealized sense, the NMR distribution is very short and long for the oil, so the oil doesn't see the pore wall, if you will, because the wall is away. So it's a very long component. Same pore network, and we add more oil. The oil will begin to see the pore wall. I know these are kind of loose terms, but it tries to interact with the pore wall, and the oil will get shorter in T2. No, it will move to the left. Of course, the water will simply get smaller. So what it is during a drainage cycle, add oil to the sample, and the oil moves left, we can say with certainty that rock is water wet. So there is a wettability indicator here. And I've shown a real-world example in which we've done it, and that is detect oil during area drainage. In other words, we've already the emission cycle, so we're adding oil to the sample. So we would start with the black, move the blue to the red, and experiment with something unique, which we can do in the laboratory, which of course you can't do downhole, and that is the water we've used in this instance is deuterium oxide. So what is deuterium oxide? Well, it's just regular water, but the hydrogen happens to have an extra neutron. What does that do for us? From our perspective, that particular type of hydrogen gives us no signal, so hydrogen becomes invisible. So experiment so that we D2O, deuterium oxide, we won't see the water, we'll only see the oil. So we're not overlapping peaks as I described earlier, we can only see the oil. So of course, everything easier to interpret. So in this example, as we add oil, the peak is moving to the right. It's becoming longer, which means it's tending towards the middle, which means contact with the pore wall, and then slowly moving towards the center of the pore as we add more. So it's slightly oil wet, and that was confirmed by USBM and other measurements. Look at some more complicated measurements. You may have seen these in the literature or on your logging tool, and these are known as 2D maps. And it seems to be, sometimes there was confusion associated with this because they're more complicated to understand. But think of it, what we have on this axis is one NMR property called T2, which I've already shown you in quite a lot of detail. In this case, we have diffusion. So diffusion, what is diffusion? Diffusion is the mobility of the hydrogen. Mobility. So at the molecule level, how well can that molecule move? How free is it to move? As you might expect, a short molecule like water, the move is good, so the diffusion is larger. When you move oil and it's in a longer hydrocarbon chain, the diffusion will get shorter. So in other words, it will get to a lower diffusion to help separate oil and water. Remember I showed you those overlapping peaks? For T, if we measure at the same time, we can try to separate those peaks, and indeed you can do that. So let's explain these maps, because I have a couple of them. We have the T2 and diffusion. So if we look here at this point where it's bright, and it gives us an indication of how much hydrogen we have at those values. So now here we have a signal. So the intent is the amount of signal that has this diffusion value and T2 value. Right? So here we would have signal would have, say, 800 millisecond and 1 e to the minus 9 diffusion. So it's, to get the idea is that we can tell diffusion and the T2. If you sum up all of these vertically, you have the simple T2 distribution I showed you earlier. So diffusion is very good at differentiating between oil and water because oil typically has a different mobility than water. Think of mobility like viscosity. Viscosity and mobility are somewhat interchangeable. This is a map in which we plotted two different properties again. So this is T2, but in this case we've plotted T1. And these two different lifetime signals, lifetime measurements, these T1 and T2 are annual lifetimes. To what exactly they are, this way, T2 is what people call the spin-spin relation, but T2 is affected in homogeneity of the magnetic field at molecular scale, where things are very close to that hydrogen. T1 is called the spin loss relaxation, and its scale is slightly larger than that. Now, typically trend together, so in other words, T1 is larger than the molecular scale, so its impact is further out. It's affected by surrounding molecules and environments. T2 are typically related in rocks. T1 is typically 1.5 times T2. It depends, of course. typically the case. So this is actually a fresh state shale sample, which we've done this measurement. And what we're looking at here, because this is still very early on, is this is the water in the sample, because the T1 and T2 are very similar. And this, and of course, this is what's piqued our interest, because this is definitely distinguishable and different than the question is, what is it? Well, what else is in shale that has hydrogen, right? If it's not water, you could argue it's water trapped in clay, but that's not the case. It's the organics or carbon. Now, I know this is a gaseous shale, so I know there's no hydrocarbon, liquid hydrocarbon in the reservoir. The hypothesis is this signal is the organics in the clay. So this is a good example of looking at the organics in shales. And I think it's a promise. We've got to do some more research on this, and we will. But if this is the case, it's one of the few techniques in which we can do this non-destructively in shale. Another set of experiments that, believe it or not, are probably more complicated are called exchange experiments, and these are the T2 store T2 experiments. They're in carbonate reservoirs, and you'll see why when I describe it. If we have a rock which has two distinct pore networks, in other words, small pores and we have large pores, like in a carbonate, the contact between those pore networks is quite important to understand. In other words, does the fluid that's in the small pore ever see the big pore? Important, of course, is the small pore can be quite large. It can contribute 33% of the total porosity. The permeability is going to be dominated by the connectivity in the large pore network. So how well connected the small and large pores are directly related to the production of the well. So what we do is we perform one of those T2 experiments, and then we pause the experiment halfway, and then we continue. And if something happens during that pause, what happens is we end up with a T2 that's not equal to T2. What does that mean? Well, if we put a 1-to-1 line on here, if it's a 1-to-1 line in this experiment, then nothing really is happening during that wait time. And happening, I mean, the spin in the small pores are still in the small pores, and the hydrogen is still in the pores, and the hydrogen that's in the large pores is still in the large pores. If in the small to the large pore, we'll begin to get a signal, as you can see so slightly here, off diagonal. And the intensity of this versus the intensity that stays on the pore can indicate the connectivity between the two pore networks. So it's a method to look at the exchange between pore networks. From this point on, I would like to describe a different class of NMR measurements that focus mainly on laboratory techniques involving space. So utilize spatial resolution of NMR. In other words, we're going to try to tell where that hydrogen is coming from in these images. And we do things that I call perturbation then image. In other words, we're going to do something to the rock, and then we're going to do an NMR measurement, something to the rock, and do another NMR measurement. And we can, depending on what something is, we can tell things about capillary pressure. We can measure dispersion during flow studies. We can do 2 and 3 imaging in a traditional sense. So we can do imaging of people, we can do imaging of rocks. You get viscous fingering, flow fronts, all kinds of fun things. I won't describe that in this presentation. I just want to mention it. Of course, that is indeed possible. There's a new class of experiments relatively new in the last few years. But these 2D distributions I've shown you up to now, but actually resolve them in space. Now, we can do 2D distributions at each position, and I'll show you how that works here in a minute. A simple rock plug in which we've looked at the signal at different slices or positions down the rock plug. So a profile, I would call it a one-dimensional image. The rock is spun in a centrifuge, so the rock has more fluid than the other end of the rock. So this end of the rock would all have air. So we have one rock that has a lot of water, and another end of the rock that has very little water. that's where we were going with this. I'm sorry. The of use, of course, is to know where that water is. Is it in a pore? Is it in a small pore? That would be more information than just how much water is there. And we can, with techniques called spatially resolved T2. Now this is a fully saturated rock, so the T distribution is the same through the rock. So down this axis we have position, and on this we have a bunch of T2 distributions. Example in the next slide. So this is the rock I showed you first. Image now. So on the y-axis is position, axis is T2, and the E is how much hydrogen we have with those particular values at those positions. So this has been spun in a centrifuge, and we placed it in the NMR machine. The outlet face is at the top. Top we have lots of water, and at we have very little water. And not surprisingly, where we have lots of water, the big are occupied, larger pores, the longer T2s are occupied. And at the inlet, those longer, those are empty. Found, but it's a good experiment to test the technique. And this we've just a period of time and repeated the measurement many different times. If we 145 hours, which is with the saturation profile, which is uniform. In other words, the same amount of water is it's at the end. This is now equilibrium, if you will. Interesting to note is even though there's the same amount of water at one end of the rock as the other, the pores are still slightly different. So at this end, this differentially in the larger pores as opposed to this end of the rock, and the homogeneous. So that has to do with the centrifuge. So here it's at equilibrium. I mean, I don't know whether this flue will ever enter and equal out. I haven't done the measurement after months, but you can see we can get information. It's applicable to many different types of flow studies, ER studies, wettability alteration, in which to do this measurement. What I'd like to present is a capillary pressure measurement. It's something our company founded quite a long ago. And capillary pressure, again, I mentioned earlier, is that force that holds onto the fluid in the rock, so it's quite important. Additional ways of measuring capillary pressure in the lab: one's porous plate, centrifuge, all which have their advantages and disadvantages. Merchant is a destructive technique, but it's fast and expensive. It uses mercury. The pressure curve you get from it has to be translated from a pore distribution. It's probably considered the gold standard, but it's a very long experiment. For in a tight gas field, it can take a year or more to get a measurement. And in the middle, we're using real fluids, but we use centrifuge forces to speed things up. And I think it uses the centrifuge as well, so I'll just describe that technique in a little more detail. Centrifuge measurement, we have a plug, we'll fill it with brine and we'll spin it in the centrifuge. Wait till water stops coming out of the rock, in other words, it reaches equilibrium. We'll average saturation in the rock. Bremner was nice enough to tell us what the inlet saturation was through this equation many years ago. Equations that I don't know, but they're Forbes and whatnot, in which they'll take that average saturation and predict the inlet saturation. So fluctuation in pressure, we have one on a cap pressure curve. We'll increase, we'll get another and another. So this tells us how much force is required to remove the fluid from rock. Experiment, we do 7 to 10 centrifuge steps, each one taking at least 1 day and sometimes 2 or 3. So the may take 20 odd days. Then our NMR is we use the spatial resolution of NMR to speed things up. Same core plug, we spin it in centrifuge, the same equation, but we realized quite quickly that predict not the the pressure at the inlet, but it can predict the pressure at any point in the rock. So all it knows is saturation at those positions. And that's what we use NMR for. So we are to the saturation at those positions. So please spin this rock in the centrifuge, wait for equilibrium, take it out, and we put it in the NMR machine and measure this curve here. We know the position at each position, we know the pressure at each position. We have 40 measured data points for centrifuge speed, thus speeding up the measurement. So if I had a slide or two, each colors comes from one centrifuge speed. So you have many data points. This experiment we did 4 centrifuge speeds just to prove the concept. The pink line with the squares is a porous plate measurement, so they correlate very well. We've done many, probably over 100 of these over the last 5 years, and they correlate very well. We typically only do 2 centrifuge speeds to fully that pressure curve, thus making the experiment 3 to 4 times faster than what's traditionally done with the traditional centrifuge. What we actually measure, of course, in the NMR machine are these profiles, pink being the fully saturated profile, and then each of these being profile the saturation after each of the centrifuge speeds. And we use the Hasselbalch equation to compute the pressure at each of these positions. Different example, this is a non-micro-Darcy rock. The trick here, of course, is getting enough pressure to remove the fluid. We did 1 centrifuge speed in this case. The conventional centrifuge, we did 5, I guess. Comparison, and they correlate quite well. There is some differences here. You argue, and we hypothesize what they are, but I won't really get into them here. But they correlate quite well. Example, just to show you that the technique is applicable to doing imbibition and secondary drainage as well. This is an oil brine experiment on drainage, secondary drainage, a sort of H the core done in imbibition and a secondary drainage. Up in this technique is what happens to the fluid after you move it from the centrifuge and put it in the NMR. So fluid redistribution. Well, the answer is, well, I've already shown you an example earlier that tells you it doesn't stay put. It does move eventually. So the question really becomes, how long do we have to do these measurements? And it depends on the permeability of the rock. The higher permeability, the quicker this fluid moves around. Case where we have a Darcy rock, or we have a couple of hours to do the measurement, which is plenty of time because the measurements typically only take 20 minutes. So we've done these redistributions to look at the effects of this. I think I'll just leave you with is there's some extra information there that we can use, and a little bit unique to our technique, and that is capillary pressure curve. When we have lots of points on the capillary pressure curve, we can create equations backwards. So what do I mean by that? Well, at pressure point, we can convert a radius. The radius, we get the saturation change at that pressure because we have lots of data points. And the curve, which will be throat distribution. Mercury in this case, and it correlates very well. Obviously, mercury can take us down to smaller pore throats. But we have a very good indication of pore throat. And I think that is something that is a little bit unique to this technique, is for information. Thank you very much.
Thanks, Rick. So I think we can start the question and answer session. As usual, people sitting in the room can directly your question. From remote, please jot down in the chat your question. I will read the question, and of course, then we will provide a reply. We have a sort of interaction in the room, of course. from remote. Please, Shy.
The eyes.
Okay, Derek, if you can ask. Hi, I'm Nicola Bona of the labs. Derek, please show us again the slide where you change how the cutoff between free fluid and bound fluid is determined usually. Okay, again. The blue and yellow T2. Okay, this one. So the common approach is the one you calculate the area in the blue curve and define the cutoff. The word is different because if you look at the yellow curve, for example, that there are pores having a T2 of say 5 millisecond where there's free fluid. If you put a cutoff at 9, you know that all these pores in fact contain only bound fluid. So my question is there a better approach to take into account also these effects?
Yeah, there is a model other than the cutoff, I call it model, and that is in reality we don't suddenly come up on a pore in which all the fluid's going to be bound, right? So it's not, you know, micron, all the fluid is free, and then we go to 1 micron and suddenly it's all bound. That's just not a reality in nature. It's going to occur. So there does exist a model which is called a spectral cutoff. In other words, we actually use an equation for the cutoff. It'll be a line with 100% of the fluid is bound at the very short pores, but then will slowly come down into the large pores. Spectral cutoff. What we do with that is we take that line and we would then multiply it point by point with the yellow line to derive the balance. So it's gradual cutoff, if you will. It's given by a weighting function or an equation, and that's people have used that. I guess you might ask yourself, you know, why is it is a more realistic model because it's mostly what's happening in nature. But at the end of the day, hard cutoff and the spectral cutoff will give you the same amount of bound fluid. So if you're only after what is the bound fluid, then it will give you the same number in a much more simple sense.
One question, Maurizio Mele. You have mentioned that you kind of suggest fluid typing over T2 maps for fluid typing in gas shales. Understand? Do you think that the total amount of fluid in a gas shale system is enough to have a good signal for having these kind of fluid typing maps?
Can MRC enough of the fluid?
Yes, because in a gas shale system, the fluid that can be activated by an MR is small.
Yeah.
I think that the signal is enough is to have this kind of good typing with the T1, T2 mapping.
Yeah, it's interesting you should mention that. So the type of logging equipment, the logging tools are going to always lag behind the laboratory equipment. So we do a better job in the laboratory than you can do in a logging tool. So luckily the logging tools couldn't even see clays, right? So now getting to the point where they can see clays. When they start to see some of these very short that are in shales, there's fluid in the shales. The question is, can we see them? Yeah. The amount of fluid is very small. Very small, and the pores are very small, which from an NMR standpoint means that the T2 is very short, which makes them difficult to measure. So in actual fact, there's actually a large amount of fluid that is in the pores, but often the tool can't see it. I don't say to the existing logging tools. I know the companies have come up with different techniques. They're just ultra short TEs and all that sort of thing. And the goal of all of these techniques is to start to see some of those things. That's with the logging tools. What I can tell you about the laboratory equipment, the new version of laboratory equipment can definitely see those signals. Which means if the aren't there yet, they will be, right? So to answer it directly, I guess the question is, I'm not sure whether the logging tools can do it. I know lab equipment can.
From the lab. You mentioned you can distinguish the oil from the water with the air. So are you able to calculate the saturation of the fluids inside the core? I mean, at the end of a core flooding or the initial water saturation?
Yes, in order to distinguish between fluids, oil and water, the oil and water need to be different from our standpoint. If you have a light oil that's very light, its diffusion coefficient will be the same, so that we can't distinguish them. So, instances we can see them, the differentiation, and we can, yes, we can quantify how much oil, how much water. So we can look at the oil saturation and the water saturation. Or you can do additional things. If the oil and the signals have NMR properties that are similar. I showed you one in which we use duo for water, which makes it invisible. That's one trick we do. Another is we can use doping agents to move the T2. So we can put. I don't want those things. I'd rather use the actual fluids, but so we can separate them. Yes, we can quantify, but it is oil.
Marco Pirrone from Reservoir Characterization Department. It is very interesting the point that you mentioned about the to the question by Maurizio. And so you say that in that kind of plot you are pretty sure that maybe one of the signals can come from the hydrogen gas, okay, in the shale. Is it right?
On T2 map.
Yeah.
In this example, I haven't done that. Earlier in the week, T2 will be different for gas as well. So if we had gas in the system, the signal would show up here.
That's the question, because
logging tools, that's what you see.
Yeah, because sometimes for a logging tool, the first problem is to polarize the gas, because we have not so much time to wait the hydrogen to wait. The hydrogen will be following the magnetic field. Or the other problem of the hydrogen is that we know about the gas that will lower the signal of the gas. And sometimes, since we are often with the short TE, so short echo spacing, about 0.2 milliseconds, also the gas will be hopefully restricted. So I should expect that the gas will stay in the right of the...
Up here.
Yeah, exactly. So it means that maybe in a different mechanism are related to the gas, because it is absorbed or something like that. That can...
In shale, gas is going to be a little, well, can be substantially different, right? Typical T1, T2 maps on logging tools in the past have been used to distinguish between gas and fluid. As you reckon, the T gas will be long, so it's just up here somewhere, and the fluids will be down here, so we can distinguish how much gas, effective of whether we're polarizing or, times. And there's other questions involved, but the gas will be here. And the shale isn't really just sitting in a pore, right? The gas is usually in a carriage network or in organics. And that becomes is it in those oaks, right? As the pressures come, is it actually gas anymore, right? Is it liquefied? Is it on the pore wall of the liquid, right? I mean, that's what some people think. I don't know that we have all the answers yet, right? To be honest. To answer that, to get a typical T1, T2 response. I wouldn't expect that. But you could do a laboratory. I haven't done that, where you just inject gas into this rock in a pressure cell and look at the signal.
Yes, so the important point is to try to reproduce the reservoir condition, because otherwise maybe we can misinterpret the
Yeah, the reservoir conditions are very, very important, especially when dealing with gas, right? I mean, this is a native state rock. It won't have any gas because we release the pressure, the confining pressure. If we introduce gas into this system, which we can do, to see the gas in the laboratory just as you do in the downhole tool, and it would be a useful set of experiments to do.
Okay, thank you.
Any questions? Even votes? Okay. Close the session. Thank you for coming, Mr. Derek. First. I hope we can have some more chance to have you here and have some more of events. Thank you. Thank you. I remind you all the people that this kind of webinar will be is of course recorded, and registration will be ready more or less the working time on our Reservoir Cup and Lab Cup website. So thank you for coming.
Thank you.
Very green. Thank you, Nicole, and all the attendees here in the remote. Just last thing, we're going to have another webinar from in Venezuela next week in the morning, more or less 9 o'clock. See you then on the screen and here. Bye.